The PWM is a technique that controls the duty cycle. So let's see, what's a duty cycle and why do we care about it? As it turns out, a pulse width modulation signal is just a digital signal that goes between 0 and 1. It's just a square wave signal that goes 0 or 1 logic. And 1 could be whatever value it is, whether it's 5 volts, 3.3, or 1 volt. Duty cycle is, by definition, is the proportion of time that signal stays in the on position versus the total period of the whole signal. And if you write the equation for it, this is what it is. It's basically just a percentage between the on proportion versus the all proportion in here, or the total period of the pulse width modulation cycle. Okay, so let's take a few examples, or look at a few examples with different duty cycles. So in the first one in here, it tells me that 25% of the time the signal is in the on position, and of course it's going to be 75% of the time in the off position or 0 position. This duty cycle, which is 50%, it tells me it's 50% in the on, 50% in the off. And in here, it's the opposite to the first one, which is 75% in the on position, 25% in the off position. Okay, so again, the pulse width modulation is just a technique that controls this particular metric, which is the duty cycle. So why do we care? Well, we do care because of the following. Instantaneously, if you take a look at the pulse width modulation signal in here, or if you connect a device like an LED or a motor or any analog device, what it does see the instantaneous voltage. It's either going to see 0 volts or whatever 1 is. And for our purposes, we're just going to call it 0 volts in here, and we're going to call it VCC in here. Basically, that VCC could be 0, it could be, 1, 5, 3.3 volts. Let's just call it VCC. So instantaneously, that device just sees 0 and 1. But on the long run, because it's an analog device, it doesn't know that this is actually digital ones and zeros. What it does see, it sees the average voltage. Like, so if that device is monitoring that signal or is connected to this particular signal for a certain period of time, it's just gonna see the average. So the way we calculate an average voltage that device can see is borrowed from the way we actually compute expectation in probability theory. So in probability theory, it tells me that if you want to compute an expectation of a value or a random variable, let's call it v in this particular case, you just have to multiply that v by its probability. That's where this is coming from. Okay, so what are the possible values of v? Well, the possible values of the voltage, it's either 0 volt or VCC. And I know that I have to sum because of this is actually a summation signal in here. Okay, so what's the probability of VCC? Well, the probability of VCC is the probability of having a logic 1. And if you use the frequency interpretation of probability theory, that's exactly D, okay, which is the proportion of time it is in the on position. Of course, if it's D in the on position, that means it's 1 minus D in the off position. So if you do these calculations a little bit and you do the math, you will see that it's just basically D times VCC. D in here is actually the duty cycle, and VCC is that voltage in here. So what do we have in here? Well, what we have is the following. If you connect an analog device to this particular signal, that analog device will see an average voltage, and that average voltage is exactly D multiplied by VCC. So if you do change D between 0 and 1, because D is a proportion, you can get a signal that actually goes from 0 all the way to VCC volts. So that by controlling the duty cycle, you're controlling the amount of voltage, or the amount of voltage that that analog device is seeing, and in terms, it's the amount of power you're providing to that analog device. And this is why we care about duty cycle, and that metric in here is what we usually change in the pulse width modulation.